So today we're going to measure the speed of light. To do that, we need some scientific equipment like a microwave oven. Then we need some scientific chocolate chips, some scientific cardboard, and some scientific kitchen paper. So we're going to use this microwave oven and those chocolate chips to measure the speed of light. How are we going to do that? Well, this is a resonant cavity. So the microwave is just a specific wavelength of an electromagnetic radiation. So the microwave oven just emits an electromagnetic radiation in the wavelength of the microwave, which is like around of the order of a few centimeters to a few tens of centimeters. Those are the wavelengths of the microwaves. Why those? Well, because the molecules of water, they resonate at that particular frequency. So they absorb a lot of energy at that frequency. They oscillate a lot if that's a suitable frequency, and by oscillating they vibrate and they heat all the surrounding. And because all the food that we eat contain water, that's the way we're gonna heat any water for the tea or the milk that you use in your Earl Grey morning tea. So this is a resonant cavity. What is that? Well, the size of the microwave is such that it is a multiple of half of a wavelength. So you can build a resonant cavity if the size of the microwave of the cavity is half a wavelength, 1.5 wavelengths, 2 wavelengths, and so on. So because it's a resonant cavity, you have a wave going to one side and then is reflected off of the wall going backwards, so it goes back and forth, and then because of the suitable size of the resonant cavity, you're going to have constructive interference, that you're going to have some standing waves. So in those standing waves, you will have one region of the space where the oscillations are going to be maximum, some others there's not going to be oscillation at all. In those places where the resonation is the oscillation is maximum, then is where you're going to make dance those water molecules that are going to warm the whole food that you put in. So, but because you want all the food to be uniformly distributed, you have a dish that is rotating so that you don't have one portion of your chicken that is going to be very hot and the other portion of the chicken that is going to be cold. That's why you have that rotating dish. We're going to remove the rotating dish. We don't want the dish at all. And now we're going to wrap this scientific cardboard with this scientific kitchen paper. And now we're going to put the scientific chocolate chips uniformly distributed. You can use any chocolate chips. It could be dark chocolate, milk chocolate. I wouldn't use white chocolate, that's just basically fat. Now we put it here, close the microwave, and we put it shouldn't be more than a minute. And now those places, because it's not rotating, those places where there's going to be a lot of oscillation, where we have the maximum of those standing waves, the chocolate will start to melt down. Now there will be another place where it melts down, but in between there won't be any melting. Then we're going to measure that distance between one melting point to the other one, and that will give us information about the wavelength. Now we will read at the back of the microwave what is the frequency, and from there we will calculate the speed of light. Now, come here, have a look at this. So we have some regions where there is some melting, and melting. So now, I'm going to use the ruler, and where the centimeters are here, and I'm going to measure from the center of this melted part to the center of that melted part, which is about, I would say, 6.5 centimeters. So 6.5 centimeters, because that is going to be half of the wavelength of the electromagnetic radiation emitted by the microwave. Now we're going to have a look at that back here. All the microwaves indicate what is the frequency, 2450 megahertz. So that is the frequency, and I just said that was 6.5 centimeters. So let's calculate. We know that the speed of the wave, any standing wave, the speed is going to be lambda times the frequency. So we measure 6.5 as half of the wavelength. So the total wavelength is going to be 13 centimeters. So in order to measure this, calculate the speed of light, I have 13 times 10 to the negative 2, because SI units, multiplied by 2450 times to the power of 6, because that's megahertz, and I have something like 318 million meters per second, which is not that bad. It should be 300,000 kilometers per second, and this is 318,000 kilometers per second. So that's an error of less than 6%. So not bad, measuring the speed of light. And now we can eat the result of the experiment. May the science be with you.